Hey everyone, welcome to Science Sketchbook. In this video, we are doing a little review game to practice some of the following concepts shown here. So just a heads up, I will be showing the questions on screen with the timer, but I don't let the time go all the way down on most of them. So you can just pause the video if you need more time, or you can try to go for speed if you'd like to. So let's begin. Question 1. What is the index of hydrogen deficiency for this molecule? Alright, did you get it? The answer for this one was 4. Now, there are a couple of ways to solve for index of hydrogen deficiency, or IHD, so let me show you how right here. So the fastest way to do it is IHD equals pi bonds plus rings. Pi bonds are just the extra bonds, right? Like double bonds here. There are 3, and there is 1 ring as a whole, so 3 plus 1, that's 4. But let's say you're unsure of that, or you're given an empirical formula instead of a drawn-out molecule. So you can always plug it in to this formula here. All right? So check it out. We've got 6 carbons, we've got 0 nitrogens, and we've got a total of 1, 2, 3, 4, 5, 6 hydrogens, right? And no halogens shown here. So if you add these up, 12 plus 2 is 14 minus 6 over 2, 8 over 2, that's 4 as well. So that's the fail-safe way too. All right, question 2. Give me the IUPAC name of this molecule. All right, how'd you do on this? The answer was the one on the bottom right below. If you got tripped up, you might have gotten confused on where to find the parent chain. So let me show you this one. The first thing you gotta do is find the longest continuous carbon chain. So if you follow these other ways, you get 6, but if you did go all the way up to the right, you would get 7. So that's a heptane for the parent chain. Then you can highlight your substituents. Now, to find the number, you basically want to get the lowest number possible for your substituents. If you number from up on the right, you get a 3-methyl 4-isopropyl. Then you find alphabetically which one goes first, and you write it out: 4-isopropyl, 3-methyl heptane. Question 3. Give me the IUPAC name for the following molecule. Alrighty, we've got our answer in blue here. If this one was a bit confusing, remember that we are working with priority groups in this molecule, so the naming might be a little bit different. You might be tempted to find the longest chain like in the example before, but remember with priorities like alcohols, triple bonds, double bonds, you need to include them in the body of your parent chain. That's why we've highlighted this 7-carbon chain here. Priority groups go in that end name as well. So first, let's highlight those substituents again. We've got a sec-butyl, or 4-carbon chain connected on a secondary carbon, a methyl, and another methyl. Then to number it, we just have to number closer to our highest priority, which is the alcohol here. This gives us 5-sec-butyl, and then we've got 2 methyls over here. So now to put those substituents together in the name, you can go alphabetically. So you've got M and B, giving you 5-sec-butyl, 2,4-dimethyl for your substituents. Now, of course, we can't forget to number our priorities. So on carbon 6, where the triple bond begins, that's what will go in front of the ine, and 2 for the alcohol. Question 4, asking for yet another IUPAC name. Alright, so here's the answer. Now remember, bicyclic compounds have a little bit of a different system for naming, so let me remind you here. So for the parent name, you always start with bicyclo, bracket, and then the number of carbons in each component of those rings. For the carbon total, you can just sum the numbers in the brackets and then add 2. Alright, so in total, that's an oct. Of course, we do have that alcohol priority there, so that will also go in the end of the name as well. Now, the only thing different about a bicyclic compound is that you always have to start numbering at a bridgehead, and you must always circle around the largest rings first. So between these bridgeheads, if I number from the bottom, we can get alcohol on number 6. So that gives us our octan 6 all there, and then we've got our 4 for bromo and 3 for methyl. Question 5. Which ring is the most stable? Alrighty, so this one's a bit straightforward. With a lower number of carbons in the ring, you've got more torsional or angle strength. That's why cyclohexane is ideal, especially with its chair conformation. Question 6. What conformation is this Newman projection in? Alright, nice job. That is the anti-conformation. Let's take a look at it here. So our methyls were opposite, our bromines, and our hydrogens. When all like groups are opposing each other, that is called the anti-conformation. This is the most stable staggered form. Question 7. Match the Newman to its bond line structure. Alright, how'd you do on this one? I know these ones can be a bit difficult, so feel free to watch my longer video on going from bondline to Newman, but otherwise you can see how I recommend you do it here. So your front carbon in pink here, it looks kind of like an upside down Y shape, so that's what it will look like in its bondline structure. The back carbon in blue here looks like a right side up Y, 2 prongs upward and 1 stem downward. Now go ahead and replace those prongs with 1 wedge and 1 dash each. The stem of that upside down front Y shape, that is a methyl group, so you can put it on the stem in the bondline structure. But now for the prongs of the Y shape, who is going to get the wedge side? Well, since I put our front carbon on the left there, and it looks down to the right at that back carbon, you can use my mnemonic. Left to right on bondline means wedge is on the right of the Newman. Well, our bromine is on the right there, so that means it must have had the wedge. Same goes for the back carbon. Left to right, wedge is on the right, so that bromine is on the right, so it must have been the wedge. And there you go. If I solved this one too fast, remember you can always watch my longer video on how to solve this type of problem. Question 8. Choose the accurate chair flip. Remember with these, it is just the axial and equatorial positions that are flipping, not the ups and downs. And it's not a mirror image either. So with chairs, I always recommend you number first, and you can number in any direction you want. That lower peak, that's the end that's sort of pinched and pulled upwards. So you can see that light green there ends up on the high peak on the flipped chair. In your new chair, now that you know where carbon 1 ended up, number consistently. I did clockwise here. Now we can just put our substituents in the flipped chair. So we've got this bromine here, and it is in the down axial position. That means it's just going to change to the down equatorial position. The down stays the same. It just went from axial to equatorial. Now let's look at that methyl. It is in the up axial position. That means it'll flip to the up equatorial position. Again, do not change whether it's facing literally up or down. Only move from axial to equatorial. Finally, we have this tert-butyl group, and it is in the up equatorial position, so now it'll become the up axial position. And there you have it. Alright, and finally, question 9. Which chair conformation is the most stable? Alright, and there it is. So let me give you a quick reminder on chair conformation stability. So typically, more substituents on equatorial positions is more stable, but that's usually. The exception is that tert-butyl is extremely bulky, so it must be in the equatorial position for that chair to be stable, even if that ends up putting some extra substituents in axial positions. The chair on the left has 2 in axial and 1 in equatorial. The one on the right has 1 in axial and 2 in equatorial. Typically, you would assume it's the chair on the right, but we've got to make that tert-butyl more comfortable, so that's why the chair on the left is the most stable. Alright, we did it. If you need any more help, feel free to drop a comment below with any questions, or go ahead and check out my other videos with some of my tips and tricks. Well, that's it for now. I'll catch you all later. Bye.